Well, Carlos, how are you doing today?
I'm doing great. Always trying to make geothermal bigger. We need terawatt sources, so geothermal is one of the very few ones that can make it. Happy to tell you about it today.
That's awesome. That's awesome. Do you mind giving us kind of a brief bio and how you got interested in geothermal as technology?
Yeah, so I am a mechanical engineer. I am from Colombia originally, and I came to MIT as an undergrad and master's student. When I finished that, I went to work for the oil industry. I worked for Schlumberger. They are one of the largest companies providing technology for oil and gas, and not quite the oil and gas companies themselves, but the companies who provide the technologies for them. So I was always very technical, very close to what it takes to develop technology to do one of the largest human activities in history, right? Exploiting oil. Fast forward 15 years, so I've traveled all over the world, worked in many large teams all over the world, and I was increasingly seeing the need personally to transition energy. Of course, it's obvious we need to transition energy, but I was running the numbers like a good engineer and trying to see what can actually transition energy away from fossil fuels. What can actually replace the terawatts of energy we take for granted to run the world? And geothermal and nuclear were one of the very few options that could actually do it. Long story short, decided to leave the company, decided to learn venture capital, decided to fund this company when I found out some of the ideas from MIT, which we'll be talking about today, and started the journey with Quaise. So really a person that's been close to energy, very technical, having an understanding of what it takes to transition energy, taking a liking for one of the two, in my opinion, options that can actually transition energy.
That's great. That's great. And I like geothermal because it seems to solve a lot of the challenges. People talk a lot about solar, but you can't use solar when the sun doesn't shine. Wind doesn't work when the wind's not blowing. Nuclear sounds like a good option, but why geothermal over nuclear? What was your thought process there? And of course, there are like some really big
Yeah, so
regulatory problems with nuclear. Seems to be the real deal. It's like it's just disallowed from being done.
yeah, no, absolutely. So my thought process actually starts at a higher level than that. Those are human imposed things, and we can solve them. We can set our minds to it. But physics are physics, and physics will only let you do so much, right? So it really starts with that. So let me take you through that. So when you look at the world runs on 20 terawatts of energy. Forget if that's fossil or nuclear or wind or so, it doesn't
That's
matter.
what it
That's
takes.
what it takes to run our civilization today. 20 terawatts. That means 20 trillion joules per second, every second of every day. 25 years ago, it was half of that. It was 10. 50 years ago, it was 5. 20 years in the future is going to be double. It's been doubling every 25 years. And that's just a result of population growth and the things we as humans do. We discover new things that we can do with energy, and we do them. Um, so we're talking about trying to transition into a future world where we'll need at least 40 terawatts to run the world. Now, we want all of that to be clean, carbon free, because we have an issue with global warming. Everybody is starting to accept that fairly mainstream. So what does it take, or what does the world look like at 40 terawatts, and where can that come from? You look at primary energy sources. Where can it come from? And again, I'm not talking about whether it's electricity or hydrogen or it's fuel X versus fuel Y. We're talking about where does the energy come from? There's only three places where it can come from. Fossil fuels is qualified. Nuclear fuels, and there's a few of them. There's thorium, there's plutonium, there's uranium, there's hydrogen as a fusion nuclear source, and renewables, wind, solar, geothermal, hydro, tidal, all of those. But there's really three big buckets. Can they do 40 terawatts? When you look at the physics of doing 40 terawatts, you realize that only nuclear and in the renewables, only geothermal can actually do it. None of the other renewables can. It's just a physical limit. If we were to do 40 terawatts of solar, we run out of land. We have
Gotcha. It's
equally
not
disastrous.
enough.
Not an option. I mean, like, we can scale solar big time, but at 40 terawatts, we're not even close to getting there. The same goes for wind. Geothermal is the only one, right? So it's really between nuclear and geothermal. So then nuclear, what are they, right? Fission, geopolitically very, very
Very difficult.
sensitive, you know, very difficult. We've had it for a while now, and it's really not scaling because it's very difficult geopolitically for good reasons. And fusion is amazing. We need to be a fusion civilization eventually, but fusion is going to take a while, right? Even if we had fusion tomorrow, the people, the millions of workers that it will be required to scale fusion worldwide haven't been born, right? So to me, it's a solution for the second half of this century. So that leaves you with one and only one option. Geothermal, of course, I'm biased, but that was my thought process.
I think that's a great analysis, and I've never heard it put like that. I think that's a very smart way to think about it. We're breaking down how much energy do we actually need, and where's that going, and what sources can actually meet that need in a real way. What are the big challenges with geothermal? Is it like drilling technology? What's the big key piece right now that we're kind of missing that prevents it from being a mainstream source we can use?
Yeah, it's getting to it, right? So we cannot quite get to geothermal energy at the scale and the power densities that we need. So we know it's there. There's zero uncertainty about that. We know that. We know it's always there. It's always flowing, right? So it's really, the question is about getting to it and tapping it at the depth that's required to actually start a geothermal industry, a terawatt level geothermal industry. That's, in my opinion, that's the only thing. In order to get to a new frontier and open it up, you need to get to the new frontier first. If you want to colonize the moon, you have to get to the moon, period. If you want to colonize Mars, you have to get to Mars. If you want to make geothermal terawatts, you have to get to it. You have to get to that terawatt source. So I say that it's drilling and only drilling. Of course, the minute that happens, the entire humanity, very smart people will come and start to knock out the problems, because it's not the only thing you need, but it is the one gating item that you need for geothermal to actually become anything believable.
Gotcha. That makes sense. You have to get to it, and that opens the door for us to solve the rest of the challenges. I'm curious. I know just a very, very high level about ultra deep drilling. I know there's a couple different technologies. There's like rotary drilling. There's like millimeter wave drilling, impact drilling. What are the challenges with these, and what's the best approach you guys have found so far to solve some of these challenges? I don't want you to give away anything proprietary, but like in general terms.
No. Yeah, no, glad to. So again, very high level. So drilling has been around for a very long time. Consider this, 99.999% of the resources of the planet are on the surface or below the surface. That means oil and gas, that means heat, that means water, that means mineral, that means everything we as humans need to run our civilization. So drilling has always been a big, important part of human history and human progression, right? So mechanical drilling, for many, many reasons, has always been the most developed one. We start with, let's talk about the 20th century. So we start doing rotary drilling. We start doing a mechanical rotary drilling to get into oil and gas research. Before that, we were doing it for water. Maybe it wasn't quite as sophisticated. So those are basically systems where you are putting energy from the surface, because we're not going to go in the hole. Nobody's going to go in the hole. We're going to have to move things from the surface. And somehow that energy is going to go over there and crush and grind the rock. And we continue to remove the material, normally with a fluid, a mud, a liquid, and it comes out of the hole, and we keep making a deeper hole. So mechanical drilling is very well established. It goes back thousands of years, but for oil and gas, it's really developed tremendously over the last 100. So that's one. I'll come back to why that's not enough for geothermal. So variations of mechanical drilling, you have hammer drilling, like a percussion hammer. You're basically rotating and hitting the rock at the same time. It's basically doing two mechanical motions at once. It works really well for hard rock. But again, I'm going to talk about why that's not the answer for geothermal either. Then you get into novel stuff, drilling with lasers, drilling with water jets, drilling with projectiles, drilling with plasma, drilling with electric shocks, drilling with millimeter waves, drilling with microwaves. All of these things have always been fascinating to humans to do because we're always looking for a better way to do it. Now, let's talk about very deep and hot drilling. So you have to do two things to drill deep and hot. The first one is you have to be able, this is going to sound incredibly simple, but this is it. You have to get the energy from the surface to the bottom. As simple as that. When you're rotating a pipe from the surface, you're going to lose energy as you go down because that pipe is bending, rotating, there's fluid friction. By the time you get to 5, 6, 7, 10 kilometers, you're barely scraping the rock. So that's going to be a losing proposition as you go deeper and deeper.
So that's like your car. Yeah. If you've got a longer car, if you've got a rear-wheel drive car, you've got drivetrain loss with horsepower. It's the same exact thing. It's just like on a huge scale.
That's a good analogy. Yes, you're not going to be able to get the torque from the motor to the back wheels if those back wheels are a mile away, right? It's just not mechanically possible. So the second one is again, very obvious. You need to get the material out of the hole. Period, right? If you're not getting the material out of the hole, you're not making a hole. So how do we do that? Well, we crush it into small pieces and we flow. We suspend it in a mud and we flow that mud fast enough to actually carry. In the same way that a river carries pebbles. If it's flowing really fast, the pebbles move. If it's not, the pebbles sink. So that's how we do it. Now, as we go deeper and deeper and deeper, though you have to carry those particles for longer distances, and you have a hell of a time trying to pump those muds, which are usually dense, gooey, to those distances. So your pumping power starts to grow exponentially with depth. And by the time you're in 10 kilometers plus, it's going to be incredibly high. So that's just physics, right? Now, what are we doing that's different? Let's find a really, really, really efficient way to get a lot of energy from the surface to the bottom. How do we do that? In the same way that you and I are talking right now, through a fiber optic and a laser that's carrying information, we do that at a much higher power, and not lasers, but masers. All right? So a lot of people don't know these, but masers are microwave amplification to stimulate emission of radiation, just like lasers. It's microwave. So the millimeter waves travel through the pipe over very long distances very efficiently. So that's number one.
Cool.
That's physical change number one. No longer rotating anything, beam the energy to the pipe. You can get a megawatt to the bottom, even if it's 10, 20 kilometers down. And then, because you're vaporizing the rock, the particles that condense back are actually like volcanic ash. They're very fine. They're so fine that you can actually flow them back with air, with nitrogen or air.
Oh, cool.
And that greatly diminishes the physics envelope, just opens up greatly, right? On top of that, you layer other things like cost to drill, how expensive is it, but those are the consequences of opportunity cost and market dynamics, and we can talk about those too, but from a physical, to me, it's always, does the physics let you do it? Yes, so move forward. If it doesn't, don't even bother.
Right.
Because you're not going to get there no matter how you try.
Exactly. It's a hard kind of technical challenge. Glenn, do you have any questions about that?
So I really like the idea of movement of particles using air instead of water. And I think there's an angle that people aren't realizing for this. When you're talking about really big height differences, potential energy becomes really influential. So 1/2 mgh, mass times gravity times height. So think about this. At the very bottom of the ocean, you have, an Eiffel Tower of water above you, and that's crushing down on you. That's what causes the pressure at the bottom of the ocean. Now, when you're doing drilling, I'm sure that's the same thing. Imagine if the water weighed a quarter as much, you would have way less pressure. So that makes a lot of sense to me. But it's interesting that the engineering difference is you need much smaller particles to be able to move them using air instead of water. So, and I guess that's a viscosity effect, right?
Yeah. So the physics, it's the terminal velocity is really the concept here, and it depends on viscosity, but it also depends on the relative densities of the fluids. In the end, to the common experience, you can understand that if you have, a bunch of marbles versus a bunch of flour, the same mass, and you blow on them, the flour dissipates in the air, and the marbles barely move. So it has to do with the density and and the ability of the fluid to actually displace and carry the particles away. The smaller they are, the easier they are to carry away with less dense fluid, which in this case is air, right? So that is the concept that's at work there. Yes.
Just to say how important that is, our parents are friends with a former petroleum engineer, and I told him that I was taking my mechanical engineering license exam soon, and he said, "Oh, do you know the pressure change for a cubic or for like a foot distance in water?" And I said, "I have no idea," but it's something he could just tell me off the top of his head because it's so important to understand.
Yeah.
You have to pump mud down so that you can move the material out of the hole. And so I thought that was very interesting. That it was so important to him. He just had it off the top of his head.
Yeah. It's fundamental. And there's other elements like wellbore control, wellbore stability. So it's not as simple as that, but those are the two physical quantities that I always pull out as the typical things that prevent you from doing it. Or as a quick selector for physics, mechanical physics versus millimeter wave physics versus other type of physics, right? So we believe this way of doing drilling is fundamentally novel. You know, the way the drilling, vaporizing rock with energy is not new. People have been doing this with lasers and microwaves for a long time, but piecing together all of the bits of the system. Which was the contribution of MIT. MIT was the first to actually come out there and say, hey, if you combine these, and that together, here's what you have as a system. That's what I took a look at and said, whoa, this is very interesting. And I understand drilling quite well. You know, I worked in oil and gas, and we used to develop drilling systems. So I'm not naive to what it takes to drill. And this, what we're doing is not easy. But all of a sudden, you have a window that cracks open where you see a path. And that's what we pursue. We see a path forward. And our job is to try to make it work, because if it works, the world changes.
That's awesome. And I like how you've talked about this so far, where, you know, you guys have it's a novel attack on the problem. And, you know, you've actually thought through like, wow, okay, this is actually a pathway to geothermal becoming an actual energy source. It's not like, oh, we don't know, we're just going to try it. It's like, here's like a very real pathway, you know, to get there, right? To open the door, so to speak. I'm curious, how deep do we go generally? I know this is a novice question, but how deep do we go now generally for petroleum drilling, and how do we need to get to make geothermal work?
So drilling for oil and gas barely takes place below 3 kilometers. It all happens before that, because most oil and gas, more than 90% of oil and gas, is actually in sedimentary basin. Sedimentary basin is the bit that we actually live on. It's where the aquifers are, where the oil and gas is, where the water is. Below that, you have the basement, or the hard coconut shell, which is the lithosphere. So you hardly ever need to go there. Now, some places you are actually standing on it. They don't have sedimentary overburden. You know, places that have hard basaltic or granitic rock on the surface. So the location of the basement varies, but typically oil and gas that never happens, typically does not happen much below 3 kilometers. There's exceptions. There's oil reservoirs that are deeper than that, certainly. And people, and I'm talking about vertical depth, you know, so you will hear about wells that are 10 kilometers deep, but they're not really 10 kilometers deep. They are 2 kilometers deep, extending 8 kilometers to the side, which is quite impressive to do as well. But that's where we are. Now, as humans, we've drilled at almost 13 kilometer deep hole in Russia. You know, it took 20 years to drill, but that is the world record, I believe. That is impressive. And in Germany, they drill a 9.1 kilometer hole in Bavaria, which is also quite impressive. Now, these things are science experiments more than anything else, but we can actually do that. What we're trying to do is to make deep drilling in the 3, 4, 5, 6, 10, 15, 20, up to 20 kilometers mainstream. It doesn't mean you need to go 20 kilometers every time, but it means that you can get there if you need to. So let me make 2 comments about how deep and how hot. right? Because those two things tend to go hand in hand. But there's a lot of discussion about that. I believe that hotter geothermal is better geothermal. That's just physics again. The more temperature you have, the more energy you have.
Yeah.
Period. So the hotter your geothermal, the more energy you have. To the point that water wells can look like oil wells in terms of the power output, right? And that's significant. How hot then? To me, 300 to 500 degrees centigrade is sweet. It's a beautiful spot. Why that? Well, because most power plants in the world actually operate in that range.
Nice.
So if you can get to those temperatures, you can feed power plants with clean geothermal steam. Imagine the speed of transitioning energy from dirty to clean if you can actually repower power plants, right? Again, why not more than 500? Because there's not a lot more beyond 500, right? Not 600, probably not a lot of return on the investment. Why not below? Because your power density starts to be quite low, right? So you're leaving too much opportunity on the table. So 300 to 500 degrees C is really the sweet spot. Now, how deep? Well, that's just a direct result of where you are in the world. If you're in Iceland, the 300 to 500 just happens to be within the first 3 to 5 kilometers, right? So that's as deep as you drill. If you are in the United States, in the West Coast, maybe 5, 6 kilometers. If you are in the eastern side of the United States, like New York, Midwest, well, you have to go a little bit deeper because it's not a geothermically clear. You have to go maybe twice as deep. So that's where the depth comes in. Hotter geothermal is better geothermal, but deeper geothermal is more global geothermal. It just means you can do it in more places. By the time you get to 20, 95% plus of humanity can have geothermal, unlimited geothermal energy. So that's our specification. We're developing a drilling system for up to 20, up to 500. Below that also works, but that is the upper specification.
Gotcha. So once you get there, we can pretty much serve everyone's energy needs for the rest of time.
Pretty much.
Without anything else. That's super interesting. Are there? I'm assuming there's high capital cost up front, but I'm assuming those dissipate pretty quickly once you've got the well drilled. I don't know if I'm using the right terminology, but once you've done the drilling and you get things set up, I'm assuming the costs are much lower than like wind, where you've got to replace like transmissions and turbines and things like that. What does that look like?
Yeah. So we believe we can get to LCOE, so levelized cost of energy, in the $10 to $30 per megawatt hour, or 1 to 3 cents per kilowatt hour. This is competitive, or even outcompetes wind and solar in many places. The key to that is there's 3 things that really influence that price, right? And these are really the things we need to focus on. The first one, of course, is drilling. Drilling deep wells is exponentially more expensive.
Gotcha.
A well that's twice as deep will cost you 4 to 5 times more, and a well that's 4 times as deep will cost you, 10 to 20 times more. So it becomes incredibly expensive the deeper you go. So that's number one. If you change drilling costs to vary linearly with depth as opposed to exponentially with depth, you have to attack, to a great extent, the first cost driver. That's one that we're doing. And to attack that cost driver is not about drilling faster. It's about not losing as much time. The reason drilling deep costs so much is that you spend all your time drilling the pipe in and out of the hole to replace drill bits rather than drilling, right? So if you can actually do something to do that, you're already a huge part of the way there. So that's the first one. The second cost driver is the power plant. The power plants are expensive. They're low risk. People, you can beat a power plant and you get it built and permitted in 3, 5, 7 years in some cases. But it's expensive. Building power plants is expensive. Now, if you repurpose power plants, they've already built. There's 10,000 of them actually looking for a business case to survive in the next 20, 30 years as we transition out of fossil fuels. They're just scrambling to see what they do with them. What a beautiful opportunity if you can just take them and repower them. So that will drive the cost tremendously down. And the third one has to do with how much heat you can actually put out of the ground. We're talking about watts. Rock is an insulator. It's a thermal insulator. So pulling heat out of the rock is not easy. Rock holds a lot of heat, but it doesn't want to give it to you. So you actually have to increase the contact area with the rock or increase permeability to pull the heat out of the rock. So That's actually not an expensive operation, not compared to drilling and building a power plant. It's still, you're talking about billions of dollars, but not tens of millions of dollars. That is just about getting the performance on the contact area. And you'll hear things like enhanced geothermal systems, fracturing. These things are going to be important to pull the heat out of the rock at the rate that it makes sense to repower civilization.
Got it. Got it. That's super super interesting. And I'm curious how far off do you feel you guys are from getting prototypes like in the ground and using them to drill and getting like and starting that process?
Yeah, so let's see, the effort started in 2007. The company started in 2018. So all that time between '07 and 18 was very academic. It was MIT working on the foundational science. Very important process. You cannot really shortcut that.
Right.
In 2018 to now, we basically ported the technology from the university lab into a national lab, and we're operating at 10 times the power levels. So 10 kilowatts in MIT, 100 kilowatts plus at the national lab level. That allows us to do deeper holes, faster holes, and explore the drilling process more extensively. But that's still in the lab. We're still talking about meters to tens of meters holes. Now, to get out of the lab and to get into the 100 meter, 1 kilometer plus, you actually have to now build a deployable system. You need to package the technology for field operation. And that's what we're doing now. We are taking all of those components and ruggedizing them for a field operation, which is what we've done in summer. This is what we know how to do really well. And that process will see us getting the first data point in the field in the next 18 to 24 months. At that point, you start seeing the first 100-meter magnitude holes. Still far for geothermal, but quite an impressive achievement for taking the technology out of the lab. If you fast forward another 24 to 36 months, you'll start seeing that in the 1 kilometer plus range.
Nice.
That starts now to be viable for geothermal. So by 2024, 25, we should see the first extension of an existing borehole in the western side of the United States, where we take it from a bottom hole temperature of, say, 350 degrees C to maybe 500 and show that we can actually do something that today is impossible with conventional technology. So sounds like a lot of time, but actually that's pretty fast when it comes to developing these very large industrial systems. So the second part of this decade should see us in the field attempting first commercial deployments. And that probably looks like, hey, let's take a power plant in the Western Continental Divide and repower them by drilling a geothermal field around it.
Is there something special about the Western Continental Divide that makes it a good place to set this up?
Yeah. So you have to drill less deep to get to the temperatures, right? So it almost, the minute you hit the Rockies and go west, the heat sources near the surface are closer to the surface. So it's just a way to get to market with less effort and less capital expense. But again, we are designing a system that will be equally useful whether you're in the Western divide or the Eastern divide, right? It doesn't really matter. We want to do geothermal anywhere in the world, but to start, you start with the easy stuff first, right? It just makes sense.
I love that. I love that plan. Have you faced any challenges with? I get the sense that a lot of people that invest in technology solely invest in like apps and internet technology and phones and things small like this. Have you faced challenges with doing something like in the real world where it's like it's a very hard technical challenge, but you've got a really good plan, you've got a good attack on the problem. That it's not like you're just rolling dice. It's like, well, we do these things X, Y, and Z, and then this will be successful. But have you had any challenges, just talking to investors and people like that who are used to, like, you can start a software company for $100,000, but you can't transform the world's energy supply for $100K. That's not quite achievable.
You bet. Yeah, so we've raised $23 million to date, right? That's in the course of 3 years. So it's not a lot of money. Software companies raise a lot faster, a lot more. But it's not insignificant. So what I see is the world actually has investors willing to do this.
That's cool.
And there's not the majority of them, but those are very special people. Those will become incredibly good and powerful partners to the journey ahead. What they want to see, of course, is that your team is competent and can actually get this done. If anybody can get this done, is this team going to get done, right? So that's one. And two, is this worthwhile doing? It's going to be expensive and it's going to take time. And there's an opportunity cost to everything. If this succeeds, is it going to matter? And of course, when you talk about geothermal at the terawatt level with energy independence for every nation in the world, of course, it's going to be worthwhile.
Yes.
So interestingly enough, I do fundraise all the time. I talk to hundreds of investors, and I walk away with a small fraction, but those small fraction of investors willing to fund it are amazing human beings and the best partners I could possibly wish for.
That's awesome. That's awesome. You find the people who really understand like what it really means to, to implement this kind of technology. I'm curious, have you encountered any federal regulations, or I know, I think I actually found geothermal through Eli Dorado. He's super up on it. And he works on NEPA. I don't know if NEPA applies or there's other things. Are there regulations that you have to worry about and think about that are kind of onerous or you think should change?
You bet. Yeah. So we've talked to Eli. He's a dear partner to us, and we have our own internal lawyer slash MBA who is an well versed on that aspect. Right, in the United States, it changes worldwide, but in the United States, what you find is that there is legislation, there's policy in place, but it's actually not very mature. So it tends to get in the way. Now, that originates from the historical way of doing geothermal, right? When you talk about geothermal, historically, it almost always means, if not always, it means hydrothermal system, which means water is in place and you drill to get that water. So if water is in place, it means that water is connected to aquifers.
I see. People
and if you
drink
can get it out, yes, so you got to be careful, right, for good reason.
Yeah.
But it is not worse than oil and gas drilling, not worse than oil and gas drilling. Now, the geothermal we're doing is quite different. You don't drill for water, you drill for heat, and then you create a reservoir. But geothermal is geothermal, and you get bucketed in that frame. My opinion is that, number one, we need to show it works. Number two, regulation will accommodate it because, as I said at the very beginning, I don't think there's any other option. And it's obvious, it's going to be increasingly obvious as we get into the 2030s and 40s that wind and solar are actually not transitioning energy at the rate we need it to. So it's going to clear the way. If you want to put it really simple, if you treated geothermal the same way that you treated oil and gas, you're done. You're done from a regulatory perspective.
Gotcha.
Right? That's it. It's that simple. If you could bucket geothermal with oil and gas, for better or worse, you're done with the regulation landscape.
Got it.
This leads to a really good technical question. You said you're not drilling for water. That means you're using a refrigerant, is what I'm guessing. Or your conductive material isn't water, is what I'm guessing. And it's not air because air is a really good insulator.
That's right. We put the water in. We don't drill for it, but once we've drilled and touched the rock, we put water in and get it back.
Ah, that's interesting. Do you have to pump it, or does the change in, or does hot water just rise? Okay.
It does rise. Right? So there's you'll hear people talk about a thermosiphon effect, which is the way geysers work. So yes, it rises because of density difference, but you probably need to pump a little bit because you want the rate, the heat rate is what determines the economics of the development, which means you probably want to boost it a little bit with pumps, right? But you're talking about for every 100 megawatts of thermal energy, you probably need to spend 1%, so 1 megawatt with pumping, which is very, very low compared to everything else. So your penalty on moving water through the system is relatively low for all of the energy that you're getting. But water is a working fluid.
So you have a good enough heat exchanger at the bottom to make it worthwhile to pump. Is that correct?
Yeah, you need a heat exchanger, and that can take one of many forms. The simplest form simplest technically, but also the lowest return form is you put a monobore system. So water goes in through the hole, outside the hole, in an annular section, and it comes through the inside in a pipe that you have in the middle. All right. So people have those concepts, and that will work. The water will heat up, and you will pull heat from the ground, but you'll pull heat at the rate of 1 to 5, maybe 10 at those temperatures, megawatts. You can get a better heat exchanger. So how do you do that? Well, you can make it deeper and more contact with the rock. That's one way. Or you can fracture, whether it's locally or extensively. You can actually create permeability in the rock and connect several wells through that rock matrix. Sometimes you don't even need to fracture. Sometimes the fractures are already in place. You just need to overcome the closing pressure on them and prop them open, right? But that's how you create these heat exchangers. If you do this well, and believe me, entire nations are trying to do this. Entire nations see the value of these and are trying to do it, including the United States. When you create a good heat exchanger, you are talking about pulling 50 megawatts of thermal energy per well, per 8-inch well bore, for 50 years, right?
Wow.
Incredible.
So what type of changes in what type of delta T are you talking about? How hot of, I guess, water can you get out at the surface? Because you're going to lose some temperature to as it's coming out the well, right?
Yeah, the goal is to, in our case, we want supercritical water at the wellhead.
Wow.
Or close to. We can have it subcritical or slightly above supercritical, but that's what we want on the exit. Why is that? Well, because the supercritical phase is very low viscosity, so it flows very easily. You don't need as much pumping energy to put it through the system. It's also very high density, so its mass is high. It actually carries a lot of energy in its molecules. And 3, it actually converts incredibly efficiently to electricity when you run it through a turbine. So that's the Goldilocks. If you can do that, you have the best possible embodiment. So what does that mean? It means that down there at the bottom, it has to be more than supercritical. It probably needs to be, 450, 500 degrees C. That's what we talk about, those temperatures. You also want to avoid phase changes on the way in and out. When you allow water to change phase, like from liquid to gas, a lot of energy actually goes into the rearrangement of the molecules and not into the useful work you want to do. So you want to keep the pressures relatively high to keep water from changing phase. It will change from liquid to supercritical in the rock and then to steam in the turbine, which is outside the well. So that's the typical specification. You lose heat on the way up, you gain heat on the way down, but all things considered, you're talking about 50 megawatts of thermal energy per well by the time you're done with something like this.
So if you can get supercritical vapor at the surface, which is really impressive, can you do cogeneration? Like in an industrial setting, I could see, steam is a very useful product.
Yeah.
You can.
You can, yes. So whether it's supercritical or not, if you get water hot enough, you can do a lot of useful things with it, right? So let's talk about the supercritical. So what would you do with that? Well, you pipe it. You don't vent it, right? You pipe it. It's always contained. You pipe it to a turbine, a supercritical turbine. Right. That water changes phase in the turbine from supercritical to saturated vapor. And it produces a lot of energy in that process, electric energy, because it's moving the turbine. Well, then you take the saturated vapor and run it through a dry steam turbine, a second one, and you take a little bit more energy from that. Each of those is like 50, 40, 30% efficiency. So you're kind of squeezing the thermal energy, and the enthalpy really, out of the molecules and converting that to electricity. And as you continue to lose enthalpy or heat, then you start doing things like, hey, let's run it through an industrial process like drying pulp, or let's run it through a residential or industrial heating system, right? So The beauty of this is that you can take it from a high point and cascade it down with all of these uses in between. And by the time you're done with it, it's lukewarm water. And then you can pump it back into the hole, get it hot, repeat the cycle. Really cool.
At my university at NC State, we have these natural gas turbines, and we do exactly that. We use cogeneration to get an amazing efficiency of used energy. They make steam, which is pumped to the buildings for heat. And I took an elective where they couldn't show us because of COVID, but we walked through like the increase of thermal efficiency using cogeneration, and I was amazed. It was really, I mean, the difference between getting 50% used for electricity and then, okay, what else do we do with the steam versus, using about 90% of the energy which is released from the fuel from combustion.
Right. So now now in this case, there's no fuel. It comes from the ground. Well, there is a fuel. It's the radioactive decay in the Earth's crust, right? That is the fuel.
Right.
But it's there no matter what, whether we tap into it or not, right? So yes, that's the idea. And chances are that everybody listening to these, or the vast majority of people listening to these, are getting their energy from a thermal generation plant. There is steam involved in that cycle because that's what we built in the 20th century. So we're just basically saying, hey, let's just change the boilers, right? The problem is not the thermal plant. The problem is the boiler burning carbon. Just change that. Only that. Leave everything else in there.
Yeah, we have free boilers. They're just very far away underground.
It's just hard to get to. That's great. Well, Glenn, do you have any more questions for Carlos here?
I'm kind of interested in, do you put any effort into insulation on the way up? Or do you have two separate holes, one to put water down and one to bring water up?
You do put insulation. It makes things better, right? You don't always have to do it, but it makes things better, right? Because the less energy you lose to the rock, the more energy you get to use for your power or industrial heating uses. Now, rock is a thermal insulator. So by design, you are already insulated quite well. You just can do a little bit better by doing fancy things. If it's really, really deep, you probably do want to put insulation, not all the way, only on the upper portions, because the places where you will lose the most energy is where the difference in temperature between the fluid and the rock is the highest. So if you're close to the surface, so the ground could be at 100 degrees Fahrenheit, and the water is supercritical. So you will lose a lot of energy if you don't insulate. So you'll probably benefit tremendously from insulating the upper portions. Now, the deeper portions, you don't need to insulate because the difference in temperature is not that dramatic. But it makes things better.
Awesome. This is more of a Will-like question, but overrated or underrated, the idea of having like a low energy society, which is a lot of what the green movement has been pushing, like when I was growing up. They're saying, make sure you turn your lights off and make sure you turn off your tap when you're brushing your teeth. I understand we want to be efficient, but do you think we can just design our societies to be low energy, or do you think we need really high power capabilities of producing energy for the future?
I think we need a lot of energy to prosper. Right? I think it goes hand in hand with quality of living and prosperity. Yes, we can always do better with efficiency, but the energy that we consume doesn't come from the typical places you think of, right? Turning off lights, doing things with your chargers for your phones, those things help, but they help very little. The energy really is embodied in the world around you. So look around you. Your clothes, your glasses, your iPhone, your computer screen, your bed, everything, your floors, the wood, the wall, everything is possible because of the tremendous amount of energy available to the civilization. You make it more energy efficient, it helps, But if you want to drastically reduce energy use, it means all of those things go away. All of them. All of them. There's no materials to build with. There's no transportation methods to use. There's no food, right? The food to eat. Have you ever stopped to think about what's in front of you on your plate? Yeah, it's not just potatoes. It's 100 different things that come from all over the world. So I don't believe that we will see a lower energy use as a civilization going forward. I think it goes hand in hand with prosperity, and it's just the evolution of the human species, right? If we're not doing that, if we're not consuming more energy, it's because we're not prospering. It is because Mother Nature hit us in the head and we had to back off and we basically devolved the civilization. So that is my view. I very strongly believe in it. I think energy is prosperity, right? And if you want to use less energy, it's equal to saying you're going to be less prosperous, period.
Definitely. And providing cheap energy that's clean and we can use forever. I mean, it's super important. It's super important for the future of humanity. Definitely. Well, Carlos, thank you so much for coming on. Where should we send people? Where should people check out your work? And if people want to learn more about geothermal, where should they go?
Yeah, so our work, Quaise.energy, Quaise, that's the name of the company, .energy. We have a little bit in there, but that's the entry point for what we're doing. If you want to know more about geothermal, I think a very good reference is Pivot 2021. So Jamie Beard, Google that name, Janie, Beard, Beard. She is an amazing champion for geothermal. And she's put these conferences over time where people from all over the world and all backgrounds talk about geothermal. There's a whole series, weeks of videos on YouTube where you can start watching all aspects, technical, regulatory, policy, equality, energy transition, right? So I couldn't point you to a better resource as a start than that, right? Pivot 2021, Jamie Beard, and Quaise.energy specifically for us.
Awesome. I'll make sure everybody has a link to this in the description. Well, Carlos, thank you so much for taking the time. I really appreciate it.
All right. Thank you for having me. Thanks for your curiosity and trying to elevate the voice of geothermal.
Absolutely.